So hello everybody. I'm Gerd Hoffmann, working for Red Hat, and I've stepped up recently caring about the USB subsystem in QEMU, and I'm going to talk a bit about it. So how it looked 1 year ago, it was pretty much unmaintained, and patches for USB which went to the Q devil list often got lost because there was nobody looking after USB. We only had USB 1.1 support. We had no migration support for USB devices. And what a lot of people noticed, that if you enable the USB tablet, so you have an absolute pointer in your word manager interface, then the virtual machine starts burning most of the CPU. So I want to go to talk about what has changed in the last half year and what we are going to do or what I'm planning to do for the future. But let's start first with some very basic information about USB. So this is how a USB device looks like. If you list them with LS USB, you can give the .v switch for both, and then it will dump all the descriptors. And there you can see the device identifies itself. Every USB device can have several configurations. That's a configuration descriptor. Most USB devices have just one. And for configurations, operating system can select one of them, and that one will be active. And it can be used for stuff like that, that its device can present itself as CD-ROM with drivers, for example, and then the driver can switch the configuration, and then it presents itself as something completely different. Then each configuration can have some interfaces. Again, most devices have just one, but for example, some USB webcams with audio support, they have one interface for the video part and one interface for the audio part. And the last piece is every USB has several, every interface has several endpoints, one or more of them. In that case, this is just the USB mouse, the USB tablet emulated by QEMU. It has just a single endpoint. Most devices have a few more endpoints. So every USB device can have up to 16 endpoints, and there are 4 different types. There's a control endpoint. Every device implements the control endpoint. It's the number 0, and that can be used, for example, to fetch all those descriptors to figure out what for kind of device. There are bulk endpoints, which are used to transfer bulky data. For example, USB storage uses bulk endpoints. There are interrupt endpoints, which are used by devices which signal something or send some data usually on some external event to the host. For example, the human interface devices have some interrupt endpoints. And there are also asynchronous endpoints which are used for data streams, usually used by audio and video devices. So one interesting thing is that all endpoint transfers are started by the host. So it's not like your USB mouse can just start a transfer. If it got an event, it has to wait for the host to initiate that transfer. And the result is this. That the USB controller is polling the USB tablet in regular intervals and asking whenever it wants to transfer some data on that interrupt endpoint. And the USB tablet says, no, I don't have any, and then it continues asking. And if you click on your tablet or move the pointers, then you get some event, and the next time the host adapter polls the USB tablet, it will send over the data, and the host controller will send out an interrupt informing the guest operating system that it actually got some data from the tablet, and then will continue polling the tablet And most of the time, there wouldn't be any event, but still the USB controller is constantly pulling that. And well, on real hardware, on bare metal isn't a big problem. It's all done in hardware. But in QEMU, we are actually emulating the hardware. And that's why it takes quite a bit of CPU time to emulate this USB thing, because you're doing this constant polling. So, okay, what did change in the QEMU when it comes to USB? Start talking about what changed in the 0.14 release. We had a major internal overhaul of the USB descriptors. There used to be just some binary blob, which was just a binary representation of the descriptors, which you just could copy over to the guest operating system. And I've moved over this to have some nice structs where all the properties were in and some code to actually generate the binary representation from that, which was a nice cleanup. It's also quite useful for the other speed descriptors, which you have with USB 2.0. In USB 2.0 device, you can ask what capabilities it would have if it would run in the other speed. So if you plug in your USB 2.0 device into a USB 1.1 port, the operating system can still figure out what the device would be able to do if it would run on a USB 2.0 port. And this descriptor format is slightly different, and it's just easier to just generate this from scratch, from the structures, instead of trying to binary patch the blob representation you have there. And it's also easier for the USB subsystem itself to figure out what properties a device has. And this allows to move some common code, like fetching the descriptors, move all this to common code instead of having every virtual device implement its own largely cut and pasted way to send the descriptors to the guest operating system. We also got support for physical port addressing. In USB, we have basically two kinds of addresses. One is the USB devices form some kind of tree. And when you look at the physical hierarchy, you have the root hub, which belongs to the host adapter, where you have a number of ports. And if you plug in a USB hub, you'll start creating a tree like this. And the physical address of your USB device is just along this path. If you have a USB hub, the devices get an address like this. It means it's plugged into the second port of the root hub and then the first port of the hub, of the USB hub plugged into the other port. And there's also the device address, which is assigned by the guest operating system. And that's just a number, which must be unique above the whole tree. So, and you can now create, when you're creating a USB device using -device, you can actually specify which port you want to plug it into, and to create this one and then plug in the device into that port, you can use this syntax. First, say you plug the hub into this one port and then just extending it like this to plug more devices into the USB hub. That wasn't possible in older QEMU versions, where QEMU used to just random select or just pick the very first free port it could find to plug in the USB device.
Question.
Yes?
If there's a port or if there's a hub plugged into that port, will that cascade? Will you support multiple things off of that physical port?
Yes, you can just plug in one more hub into that with the very same syntax. You just say USB hub and then port 2.2. And then if you want, again, plug in devices into that hub, you say 2.2.3 or something like that. And so you can just...
So you have to specify ahead of time if it's a device or if it's a...
Yes.
I think we're talking about USB redirection, so redirecting a real USB device to a virtual machine. Or am I misunderstanding you?
Okay, that was yes, that's what I'm referring to.
Yeah, now USB redirection is only supported at the device level. So you cannot redirect an entire hub and everything that is attached to it. Then you must redirect every device which is attached to the hub separately.
So what we also got is migration support. Surprisingly, that simply wasn't present in older use QEMU devices, and even more surprising, we got almost no problems because of that. So we are lucky that there are a lot of buggy USB devices out there. So the guest operating system figures the USB device stops responding just because it didn't remember its device address. And so the guest operating systems, at least the more recent ones, just reset the device and go on. And Linux kernel logs a message, oh, the device has been disconnected. That's the only way to figure, okay, this has happened. And then it goes on and uses your USB tablet, and you don't notice that there isn't no migration support at all. But it's now fixed. We have migration support for the hub and also for the human interface devices. And we still have to do that for the other ones. And starting with the 0.15 release, they at least tagged as being having no migration support. If you try to migrate a virtual machine with, for example, a USB storage device attached, QEMU will complain and say, oh, I can't do that because that device doesn't support migration. Another important thing is remote backup. This is one way to address this polling problem, which burns all your CPU time. Devices can actually send wake-up requests to the hub they are connected to, or to the root hub in case they are just directly connected, and and that way tell the root controller that they want to transfer some data. And then the guest operating system, or on bare metal, the operating system can resume the USB bus and then ask the device what data it wants to transfer. And this allows the operating system to just suspend the complete USB bus and say the host controller to stop any USB operations, and then just waits for this wake-up event. And if that happens, QEMU don't has to burn CPU cycles to do this constant polling. And also, if it's done on real hardware, the power consumption of the USB controller goes down, so it's not just useful for virtualization. The QEMU USB hub and human interface devices support it now. One problem is that again, there's a lot of buggy hardware out there, and that's why the operating systems don't support that by default. Because if they would do, a number of devices would just stop working. And we have some UDEF rules in upstream, which has some rules to just match the QEMU human interface devices and enable remote backup for them. So if you have a recent Linux distribution, it's just enabled by default.
Actually, Windows 7 uses it. Windows 7 uses it.
Does it by default? Oh, nice. So there's a hope that the buggy devices will go away because they stop working in Windows 7. So that's the effect if you look at PowerTop. The number of wake-ups QEMU is doing just to do this polling. And if remote wake-up is active and the guest operating system just suspends the USB bus, then it goes down significantly. In Linux, it is 2 seconds by default, so if you don't move your mouse for 2 seconds and remote backup is enabled, then Linux will just suspend the bus and it will wake up when the next event comes in. USB device emulation got some improvements. The USB storage device actually got 2.0 support, which wasn't that helpful in that release because 2.0 host adapter wasn't present yet. So the only thing you would notice that the Linux kernel says, oh, you have plugged in a high-speed device, and you have plugged it into a low-speed port or into a full-speed port, and it doesn't run at full speed. That's the only thing you notice from that. And the USB pass-through driver, called USB host, got a number of improvements, especially when it comes to isochronous transfers. It does some buffering now, so it can keep the data stream running, so it can transfer the data to the guest while the host adapter is still filling the next buffers. And that got several webcams working with USB pass-through, and as usual, a bunch of bug fixes. So what is new in the just released 0.15 QML version? The big thing is finally USB 2.0 support is there, including the host adapter emulation, so you can actually use your USB storage device at full speed. As mentioned, some of this was merged in 0.13 already. And also the USB host emulation or the pass-through code got a bunch of fixes and adaptations which are needed to make 2.0 devices work with pass-through. We also got companion controller support. That's an interesting thing. The USB 2.0 controller just can handle USB 2.0 devices and not the older, slower ones. And those are just handed off to so-called companion controllers. And in case of Intel machines, usually look like this, that you have a single 2.0 controller with 6 ports and 3 companion controllers with 2 ports each. They are linked up like this. And we actually can handle this because those 1.1 controllers just register them instead of providing a USB bus of its own. They just register with the 2.0 controller and say, oh, I'm a companion controller for these ports. And then the 2.0 controller emulation just looks at the port owner bits set by the guest operating system and then hands off the device to the companion controller or not, depending on what the guest operating system requested. It's a bit difficult to create those devices because you have to set a bunch of QDEV properties correctly to link up all the ports correctly. And the easiest way to do this is just use a config file with a chip with QEMU, and this also in the Git tree, of course. Just say QEMU read config, and it has a bunch of config entries which will just create all those 4 controllers and hook them up correctly so that you have a single USB bus which can handle both USB 2.0 and USB 1.1 devices. So we also got USB redirection support, which was mentioned today already in the SPICE talk. Upstream, we have support to redirect devices over TCP. And as mentioned, it will come soon to also use SPICE as transport for USB. So you can plug in your device into the machine where you're running a SPICE client on, and the virtual machine you are connected to will just see the device. So we got a few more changes, which are not in any release yet. They're just committed to Git master. One thing is we're using scatter-getter lists now. That's especially important for USB 2.0, which can have quite large transfers, which can span multiple pages. And so the USB packet struct, which used to have just a linear buffer, has an I/O vec now. And so we can just map the guest buffers and pass them on in form of an I/O vec to the device emulation, which then can fill in stuff without copying stuff. And it also simplifies stuff when adding migration support to the devices which don't have migration support yet, because the buffer just sits in guest memory and we don't have to worry how to migrate it. And we've separated out the human interface device code, because that human interface device, the human interface protocol, which is used by USB devices, also has other users, for example, Bluetooth. And Bluetooth used to just create a fake USB device just to be able to reuse that code. And now we have some clean separation that Bluetooth can just use the human interface device code directly without doing crazy stuff with USB just to avoid cut and paste. So, future plan, oh, some typo in there. Future plans for USB. One quite important thing is that we need to improve the endpoint handling. So you remember this fancy graphic from the earlier slides. And what we are doing today in QEMU, each time the 1.1 controller got a request from the guest operating system to pull the USB tablet in the data structures, we're actually calling into the USB tablet and asking the USB tablet, do you have some data for us? And that clearly has to improve, I want to maintain the state of the USB endpoints at USB bus level and have some notification calls so that the USB tablet, if it gets events, it just signals the host controller emulation that this endpoint got some data. So the USB host adapter emulation doesn't actually has to call, and just has to look up what the current state is. And then we can try to optimize the CPU overhead. It's a bit difficult for the USB 1.1 controller. It's a lot easier for the 3.0 USB controllers because they have a very different hardware design. Here's how it looks like for the 1.1 controller. The main data structure is this, you have a frame list. USB has this frame rate with 1,000 frames per second. And the guest operating system gives the host adapter just this frame list, and which exactly says on which frame what the host adapter should do, and that points to a transfer descriptor where it's listed which device this transfer is to and which endpoint and the data size and so on, and also the pointer to the actual buffer, and then a link to the next transfer descriptor, so you can schedule multiple transfers for one USB frame. And to emulate that, there's not much you can do to optimize that, because for correctness reasons, you just have to work this list in a timely manner and just look up what the guest operating system wants you to do. You can try to batch a bit maybe, that you don't wake up on every single frame, but you say you process 2 or 4 frames at once. But that's about it you can do. And in contrast, the USB 3.0 controllers look very different. There's a central data structure as a device context. Each device which gets plugged into such a controller gets a device context created by the guest operating system. There's an array pointing to the actual device context, and each device context again has context for all the endpoints the device has. And this points again to the transfer request blocks, where the guest operating system just can fill in what it wants the host controller to do. And of the guest operating system adds some new entries to this transferring. It actually pings the host adapter that it's something new to do. And that is a lot easier to emulate in a fully event-driven manner without just waking up very frequently to just look if there's something new to do. So having USB 3.0 controller emulation isn't just useful to get USB 3.0 support, but also because CPU overhead to emulate such an host controller is probably much lower than emulating a USB 1.1 controller. So the remaining to-do list items I have, of course, I mentioned it multiple times already. There's still some devices don't have migration support. We want to fix that. The USB 3.0 emulation, there's already some code from Hector, and this supports only device pass-through and sidesteps all the issues I've just listed. The USB stack and QEMU has by just winding up libUSB directly. So it's a start, but it needs quite some work to get that in a mergeable state. The structs for the USB descriptors, which I've introduced, could be used more to move some emulation code to command code out of the individual device emulations. And what would also be useful, I think, would be to switch the USB host driver, the pass-through driver, to just use libUSB instead of talking to USBFS directly, which would solve the portability problems. For example, right now we have one driver for Linux and another one for BSD, and we could just switch to a single one if we would use libUSB and hand off all the portability problems to libUSB. So I think that's it. Yeah. Any questions?